Anytime we ask software to perform a linear regression, it will happily give us some output. Its job is to slave away and to produce an intercept and a slope, regardless of what the data might look like and regardless of how well the line really fits. So if you tell the software to do a linear regression, it will always give you an answer. But so it's up to us to assess how well that answer is really going to work in practice. Some models will be very good at predicting and some will not. Here's some examples of uh, two different linear fits. We've got this one over here, and let's say I'm just gonna take a guess and say that this came up with y is equal to 22 minus 2 times x. Okay, that's the model. And so we've got a slope of -2, for that line there, and we got an intercept of 22. So it's hitting the y-axis over here at 22. Okay, so there's our model. Okay, so now we can use predictions. We can make predictions using this. Here is another model, another regression that was done, and I'm guessing that the line here is 22 minus 2x. Okay, so once again, we have an intercept of 22 right there and a slope of -2. Okay, but we can tell by looking at the data that this one is a lot better than this one. Okay, so this is a really good model fit, and this is a really bad one. So, but once again, the output was identical. So what we need to be aware of is that some of these lines are going to fit the data very nicely and consequently provide you good, accurate prediction, and some will not be very good at all. You see this is not going to accurately predict. We've got this kind of crazy leverage point out here, and it's way it's just off completely. Okay, so what this lecture is about is taking that output that we got from Excel and then using it to evaluate the model fit. Are we closer to this situation or to this one? And based on our evaluation of that, of how well that line fits that data, we can either say we have a successful model that we can put into deployment, or we just have to trash the whole thing and come up with some kind of other model. Okay. Now the fundamental measure that we can use to to evaluate our model is something called the residual. So remember that we're coming up with a line, and this line is going to be off by a certain amount. So this amount right here is the residual for that particular observation. So these distances right here. And remember that we're doing, when we do ordinary least squares estimation, we are trying to come up with a line that makes these as small as possible. Okay, so it's minimizing the squared residuals here. Okay, so we want to we'll define the residual as the actual observed y, and this could have a little subscript, minus what our model would predict. Okay, so what our model would predict for this point, for example, would be right there on the line, and we are going to subtract, this is the actual, the y that we observed there, and this is what our model would estimate. And we're going to take this and subtract this, and that's going to be our residual. Okay, so I'm going to go back to our housing data model, and we're going to start evaluating this line in terms of how much it will tell us. I'm just going to we see, by inspection that this looks to be a fairly good line. I've seen in practice, much worse fits than this, but so this is actually pretty nice. But let's go ahead and quantify how nice this line is. So let's start by getting that residual. Okay, so our residual is going to be the difference between what. So we're going to take the actual house price at this square feet, and we're going to subtract what our model would have predicted for that size square feet. Okay, so this was our slope and intercept that were estimated. So there's the line, and we're going to use these two to see, well, what would our model have predicted for this? Okay, so we're going to call this y hat, right? So that's what we would have predicted for this. And so we're going to set this equal to the intercept plus the slope times this square feet. Okay, so we're just applying that equation. And so what we see here is that our model said that a 1,400 square foot house should be 251,000. Okay, and we see based on our data that estimate was a little bit high. Okay, I'm going to come back here and edit these so that they are absolute references. So I'm going to reuse this. I'm going to reuse the slope and intercept. So I'm going to make these absolute so that I can copy this down and see what my model would have said for all of these square footage. Okay, so we see that this one was a little bit high and this one was low. So for 1,600 square feet, our model said, well, that should be a $273,000 house, but it turned out to be 312. And we see this one was a little bit high. This one was very close, but it was a little bit low. Okay, so what we would like to do is to go ahead and write down these residuals. How far off are these values? And this will give us some idea of the magnitude of our errors. Okay, so let's say okay, we're going to do the observed minus what we predicted. So that's how we define our residual. Okay, so we see, so this negative residual indicates that our estimate was above the actual observed value. Or you could think of it this way, that the actual observed value was 6.9 below what we estimated. Okay, so we're going to do the residuals the same way for all of these other ones. Okay, all right. Now, if we wanted to get some idea of how good of a model this was, one thing we might consider doing is to add up all these residuals. Okay, if we add these up, how far off were they? Or maybe we could say, well, what's the average residual? But that's not going to work, because the way ordinary least squares comes up with these estimates, it actually, if we add all these up, we're going to be near zero. Okay, so that's not going to work. So in the past, when we've had this case where we've had negatives and positives together, it worked to simply square them. Okay, so let's go ahead and square the residuals. Okay, so call this squared residual. Okay, so it's just going to be this times itself. Okay, and I'll just copy that down again. Okay, all right, so now maybe what I can do is just say, okay, well, I'm going to use this number as a way of understanding how big my residuals are. I'm just going to add all these up. So I'm just going to do, and I can click auto sum here, be a shortcut for all this. Okay, so what should we call this number? Let's call it sum of squared error. Okay, so that's what we did. We took how far off we were, that is our residual, we squared it, and then we added them all up. So this will be our sum of squared error. That's what we'll call it. Okay, now what we would like to do then is to figure out, well, how big is this error in relation to how much of our prediction is not error, okay? So we want to know how much of the variability in the actual y is our estimate of y picking up. So first thing we need to know is, what's the variability of y? And the way we do that is we can do a variance, right? So we really want to be able to explain, to say, how much of the variance in y are we explaining with our estimate of y? So if our y had a lot of variability, but our y hat did not have much variability at all, let's say it always output 5, then we'd be able to say, well, it's really not doing a good job of predicting what the real y would be. Okay, so we want to quantify this. So we'll do part of the variance in house price. Really, we're just going to use the sum of the squared, sum of squares, that numerator part of the variance. So in order to get that, I need to know the mean y. And so that's just going to be the average of all of these. Okay, so what's my average y? So what I want to do is sum up the square difference between the house price and the average house price. Okay, so that's my metric for the variability in the house price. Okay, so let's do that. I'm going to do equals. We're going to do the actual house price minus the mean house price, and we will square it. Okay. All right. So what we'll call this is we'll just call it square difference for now. Okay. And I want to make that the reference to the mean absolute. So I'll come back here and hit F4. Okay. And now I can copy that down. Okay. So now if we add all these up, we'll have some measure of the total variability of our original y's. Okay, so let's hit auto sum. Okay, and we have this, and what shall we call this? Well, this is the total sum of squares, so we'll do sum of squares total. So that's the name of that number right there. Okay, so again, the purpose of this is to just give us some idea of how much variation is there in our original y values. Okay, now we also want to compare this to how much variation there is in our y hats, right, in our predicted y's, which are over here. Okay, so we see that these are off, but are they retaining some of that variability, that is, that sensitivity to changes in square feet? So we'll do that. We'll call this square diff y hat. Okay, kind of an awkward name, but it looks like square diffy hat. Okay, we'll do, okay, so y hat minus the mean y. Okay, and we need that as a absolute. Okay. Actually, sorry. We want the variability. We want the mean. Okay, sorry, I forgot to square that. Okay, so we need to have the. Okay, so this is the square difference of our predictions. So copy this down. Okay, and we'll do an auto sum again. And so what is this number telling us? Well, this is telling us that this is how much variability is there in our regression model, right? So this is the sum of the squared errors. This is the total sum of squares, and this is going to be sum of squares regression. Okay, so what we want to do then is we want to compare these numbers. We want to compare, you know, this is how much variability we're capturing, right? This amount right here. This is how much we are missing out on, right? Now we want to be able to compare these sums of squares. Now, what tool did we have in the past to compare sums of squares? Well, that should sound very familiar. That is our ANOVA. Okay, so if you recall, when we did an ANOVA, we were looking at the ratio of sums of squares. Now we took those sums of squares and we divided them by degrees of freedom and got a mean sums of squares, and then took the ratio of those two. But notice that here, this is the Excel regression output for our housing model. And notice that it gave us this ANOVA table right here. What this ANOVA table is telling you is exactly what I just computed. It's telling you something about your residuals. So if we take a look back here, this thing that I called sums of squared errors, this 13665, this appears right here. Okay, so this is a sum of squared residuals. My total sum of squares here, this 32600, is right here. So that was the total sum of squares. And my sum of squares of the regression, this 18934, is right here. Okay, so all of these have to do with what the residuals tell us in terms of how much are we really explaining. Okay, so what we want to do is to see, well, is the variability that we're explaining with the regression significantly more than the variability that we're not explaining? Okay, so we're taking the ratio of this and this, and so just like before, we're going to divide it by a certain number of degrees of freedom. This is our number of independent variables, and this is the number of observations minus the number of independent variables. And we're going to take that ratio and we're going to get okay, and there's our F statistic and there's our p-value. Okay, so the first thing we have here, the first thing that we should check to see if we have a good predictive model with this simple linear regression is whether we have a significant F. Okay, so this ANOVA table summarizes all of these sums of squares and tells you that this model is predicting a significant amount of the variability in Y, in our case, the housing price. Okay, so that's stop number one. So here are all the different model evaluation tests that we're going to cover. So the first thing is the F, and this is mostly, are we explaining a significant amount of the variability in Y? Okay, so that's a significance test. It's a hypothesis test. Okay, all right. So just to summarize then, because we had a lot of numbers on the screen there. So what we did here is we partitioned the variation again. Okay, so we had a total sum of squares. So this is the total variability in the y variable, that is, how much did they differ from their mean, just add it up, and we divided that, we partitioned that variance into how much of that we were capturing with the regression, that is, that was the difference between our estimate, the y hat, and the average y, and so that was our SSR if we look back at the spreadsheet. So there's our SSR, and the error sum of squares. So we had the difference between the observed housing price and what we predicted. Okay, so this is just the squared residual here. Okay, so when we did the F test, we were taking the ratio of the mean squared regression, that is, this divided by its degrees of freedom, to the mean squared error, so this divided by its degrees of freedom. Okay, and so this gave us, this followed an F distribution. Okay, and so we just did an F test on that. Okay, now we can use these. There's another ratio that we might be interested in that uses these, these sums of squares. Okay, so we might be just simply interested in the proportion of variance explained. Okay, so how much of the total variability in y is picked up by this? Okay, so this then is just going to be, if we take the sum of the squares of the regression divided by the total sum of squares. So this is the proportion of variance explained. Well, let's calculate that on the spreadsheet. Okay, so we set this equal to the sum squares of regression divided by the total sum of squares, and it gives us 0.508. Okay, now this is another important number that helps you decide whether you have a good model. And this has a shortcut name called the R squared. Okay, so that's the ratio of our regression sum of squares and our total sum of squares. So this is the proportion of variance explained. Okay, and we can see that it's 0.58. And the way we can interpret this is we are explaining 58% of the variability in y. Okay, so you can see that this is interpretable, but it is kind of a judgment call, because you might have an R squared that's only something like 25%. Okay, so that means that the variable that you're using to predict, let's say square feet, is really only predicting like 25% of the changes in house price, which is only 1/4. So is that usable? So R squared, and let me just show you. So R squared is here on the Excel output. It's up at the top. So 0.5808. So once again, we can say 58% of variance in house price is explained by square feet. So unlike the ANOVA, so unlike the F test, which puts a significance on something, the R square is just a judgment call. And if you're satisfied explaining 58%, and that's actually 58% is quite high for a realistic R square. I recently published a paper with an R square of, I think, 11, 0.11. And for some situations, that's all you can explain. So so R squared. So now we have two ways of evaluating the overall model. We've got the F test, which is down here, which we can look up the significance value, and then the R squared, which is here. Okay, so there's one more test that we can look at to evaluate the model. Now I'll skip ahead a little bit here. Okay, so just to summarize, this is the R squared. So this was our sum of the squares of our regression divided by the total sum of squares. And here's a visual. So that R squared is going to vary everywhere from 0 to 1. So, ours was 0.5, so a little more than half. And here are some visual examples of R squareds. So this one here is, somewhere between 0 and 1. If I had to guess, this is still a pretty good prediction. This is, maybe 0.6, and this one's a little bit weaker. This one is maybe 0.3. Okay. But the point is, even though this is a negative slope, don't get confused. R squared varies from 0 to 1. It's just the quantity of variance explained. Okay. And if there is no prediction at all, if there is no relationship between your x and your y, as there is here, then your R squared is going to be 0. Okay, so it ranges from 0 to 1, where 1 is perfect and 0 is terrible. Okay, all right. So there's one more hypothesis test that we use to evaluate, and this time it's about the individual regression coefficients. Now, if we come back here, there were some columns down here in this bottom table that we ignored. We were just looking at the coefficients. That was what we used for predicting. But there are these other values over here, and these columns give you a way to evaluate variable by variable how strong a relationship is. Now, we're going to be doing multiple regression soon, where we might be looking at, in addition to square feet, we also have age of the house or its proximity, the quality of the schools. So these are all going to be variables, and we're going to have a test that will tell us, well, does this particular variable have much impact on the dependent variable? And that's what is here. So this is going to be a t-test. So you see that we're given a standard error here. Now, this is slightly different from the standard error, the mean, that you saw before. But one way to understand this is that remember that these coefficients are estimates. And they're estimates based on a sample. And presumably, if you drew another sample, you would have a slightly different estimate of the coefficient. And remember that when we were estimating the population mean from the sample mean, each sample was slightly different. And the way we quantified the difference from sample to sample was with the standard error. Now, this is calculated a little bit differently, but it's enough to know that this standard error is an estimate of how far your coefficient would be off if you drew a different sample. Okay. Now, so it turns out that the ratio, so if you take this coefficient and divide it by the standard error, that follows a t-distribution. Okay, so remember that a t-test is a lot like a regular z hypothesis test, but it allows for slightly wider tails based on sample sizes. So this is a t-test. So we are testing the null hypothesis. Let's see, I don't even know, can I write on this? Okay, so this t-test tests the null hypothesis that the coefficient, so we'll ignore the intercept, we're only interested in one, okay? And remember, a hypothesis test is always about a population parameter, that beta 1 is equal to 0. Okay, so this is a t-test, and if we can reject this, then we are rejecting the null hypothesis that this variable has no effect on house price. Okay, so again, if we fail to reject this, then that means that this square feet's not going to predict. Okay, so we are testing whether this is significantly different from 0. Okay, significantly different from 0. Okay, so then the p-value is what allows us to make that conclusion. So we see that our p-value is less than 0.05, less than 0.05, and with a p-value of less than 0.05, we can reject. So this tells us that this is significantly different from 0. It's only 0.1, but it is significantly different from 0, and therefore this variable has a significant effect on the house price, on the dependent variable. Okay, so what we're doing here with these columns here is a very quick t-test of whether this is different from 0. Okay, and this gives you a confidence interval. Okay, so this gives you a confidence interval of the estimate, and the key question here is whether it includes 0. So if our 95% confidence interval includes 0, then we fail to reject the null. But we see that our confidence interval ranges from 0.03 to 0.18. Okay, that means that this coefficient could be as low as this or as large as this. And so this doesn't include 0, so this is significantly different from 0. Okay, but the important thing is that the t-test is what we do on the individual variables. Okay, the f-test applies to the regression as a whole. R² applies to the regression as a whole, but the t-test is specifically for the individual independent variables. Okay. All right. So we've gone through and looked at the 3 main ways of evaluating model fit. That is the f-test, the R², and the t-test. One t-test for each independent variable. Now, in addition to those, if we're going to judge the quality of a model, we have to test that we're satisfying the assumptions. Okay, simple linear regression comes with a few assumptions, and we need to make sure that we're satisfying those assumptions in order for our model to be really valid. Okay, so there's 3 here. There's actually a couple more, but these pretty much sum up the most important things. So first of all, the 2 variables have to be linearly related. Okay, and this can be accomplished with a scatter plot. This is why we do the scatter plot. If you do the scatter plot and you wind up with data that goes like this, then and you try to draw a line there, that's not going to predict anything. So your scatter plot provides a nice condensed visual proof that you're satisfying this assumption, that there's at least somewhat of a linear relationship between these. Now, it might be a weak linear relationship, so the points might be scattered all over the place, but at least it's somewhat linear. Okay. Now, so there's 2 other assumptions that have to do with the residuals. Okay. First of all, the residuals should be normally distributed. And so remember, all this means is that they should be centered on 0 and somewhat bell-shaped. Okay, so you can get as strict as you want with this, doing all kinds of formal tests, Shapiro-Wilk or putting up a QQ plot, but realistically, mostly what you want is to see that your residuals are 0 and are mostly fairly close to 0, that you don't have very many values way out here. Okay, so let's go ahead and plot our residuals in Excel and see if we are satisfying that assumption. Okay, and I'm going to go ahead and let Excel do it, because you have that option for that output when you do the regression. So I'll come here, regression. Okay, so this was my Y. And this is my X. Okay, I do have the labels. And now notice down here it gives you all kinds of options for what kind of output describing your residuals. Now I'm going to go ahead and print out just the residuals themselves. We already know what they are because we printed them right here. We calculated them ourselves, but we might just want to verify that we did it right. And then also I'm going to put up these residual plots. Okay, so all right, so now notice that, so here are the residuals. So it had, -6, 38, -5. And if we look back at our sheet, we had -6, 38, -5. Okay, so that's just a, giving us the residuals, how far off our predictions are. But this one here is the one that we're going to use to decide. Okay, now, so what this is doing is it puts the, so for the square feet, so it lined up our, our square feet from 0 all the way up to 3,000. Okay, and it said that for this square feet, what kind of residual did we get when we tried to predict? Okay, and what we will notice here is that, so this line here is 0, that our residuals are fairly close to 0. Okay, so we see that most of them are near 0. And we don't have very many that are really wildly far away. We have a lot more that are closer than we have than are far away. Okay, so we see that it's centered on 0 and that they're mostly clustered around 0. Okay, so this tells us that our residuals are fairly well behaved. They're it looks like they are fairly normally distributed, and so we can be comfortable in saying that we've satisfied this assumption. Okay, now the third assumption that we need to check is that our residuals have equal variance. Okay, now it does sometimes happen when you make a residuals plot that you wind up with something that looks like this. Okay, so what this is saying is that so this is an age. So apparently this independent variable was age, and so this was tracking the residual that occurred with the observation that had this for the independent variable. And then notice that when the independent variable was fairly small, the residuals were pretty close to 0. So these are very nice residuals here. But then as this got larger, these residuals got more and more spread out. So that by the time we're way up here, this is just really wide. And so this kind of trumpet shape, this wedge shape here, this is a very bad situation. If you have residuals that look like this, then you have what's called heteroscedasticity, and you will just pretty much just say your model's not valid. You need to do something. You need to do something to fix that. Okay, you're not going to predict accurately with that. Okay, but let's go back and revisit our residuals model. And what I can see here is that, if you look at that, if we were to try to enclose these, we can see, okay, you know, they're not shaped in a big fan like that. That there's not really any pattern here. These ones up here are not any further away than these ones early on. Okay, so we can say that we have no heteroskedasticity. Okay, so we've satisfied that particular assumption of simple linear regression. Okay, so just to summarize then, in this lecture we looked at how you test the model fit, looking at the f-test, the r-squared, and the t-test on the independent variable or variables. Okay, then we also talked about checking the assumptions, and you check the linearity assumption, that is x and y can be, their relationship can be approximated with a line. You do that with a scatter plot, and then you check the assumption that you have normally distributed residuals and that you have a homoskedasticity, or constant variance of residuals, constant variance of residuals, insofar as that is actually readable. And you can just visually check these with residuals plots. Okay? All right. Good luck, and as always, I hope this helps, and let me know if you have any questions.